the first part that I want to talk about is how do we just recognize what exponential growth looks like. And typically we see math in like 4 different forms. We sometimes see it as a table, we sometimes see it as a graph, so we sometimes see it as an equation, and sometimes we have like a story situation, and it might not be written out as a paragraph or anything, but when we think through the situation, we start seeing things like it's doubling. So the layers of paper were doubling. Sometimes I think during this this coronavirus thing, when we've talked about the way the disease is growing in terms of infecting the population, we talk about how often it's doubling. That's an exponential growth situation. If it's increasing by 1% or decreasing by 1%, we're talking about an exponential growth or decay. When we see exponential growth or decay in a graph, it looks like this. And the main thing I want you to first recognize is that it's not a straight line. This is a curve that's getting steeper and steeper and steeper and steeper as we go along this curve for this exponential growth. For exponential decay, it starts off really, really steep, and actually if we kept walking up this graph, this would continue to get steep, 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 kind of takes off like a rocket. And then gets shallower and shallower and shallower. And we talked a little bit about this, the way that this approaches that x-axis. We talk about how that approaches it, but it never quite hits it. When we see a situation that has exponential growth or decay, one of the things that we need to start to recognize is that it's not going to be, let's say this is 2, 4, 6, 8, 10. It's not going to be a situation like this. It's going to have something consistent and predictable. But this table that I just created would be a linear situation. This is adding to every step that we take. That has a constant rate of change. That's a linear situation. This would be linear. To contrast that, again, we're talking about a situation that has a predictable pattern. And so I could create one, let's see here, 1, 2, 3, 4. And let's say we start this pattern again with 2. But this time what we're going to be thinking about is how much we multiply by. And so for example, let's say this had a scale factor of 2 here. Again, 2 times 2 is 4, but then here, times 2 is 8, and then again times 2 is 16, and 32, and so on and so forth. So what we're talking about here is an exponential growth. This is multiplying by 2. We could also have exponential decay. If, for example, I was dividing by 2 each time, and maybe we start really big like this graph does, and then divide by 2, divide by 2, divide by 2. That would be exponential decay. In any case, once we start to recognize this exponential growth in a table, in a graph, or in the situation, the equation that models that situation is going to look like this. And what it's going to have is this A is going to be our starting point, which, just like in a linear situation, is our y-intercept. It's going to be this place where x equals 0. That's going to be A. Here A would be 2. Then this B, the scale factor, becomes what we're raising to the x power. This is our scale factor for the table. Now, in another video, I will talk a little bit more about how to find that scale factor if it's not given to you or if it's not obvious. The other way that we see an exponential equation written is when we're increasing by a percent, and actually we would write this percent as a decimal. When we actually use it in the equation, or if we're decreasing by a percent. And so again, this rate would be what percent it's increasing by or decreasing by. And again, that's in this language of situations that we might run into. So that's just a quick look at the way that we recognize what exponential growth looks like when we see it, so that we can start to use those exponential tools to do that math.